Hello, hello Hamza and Nida. So today we'll start dual nature of matter and radiation. Dual nature of matter and radiation. Okay, and wave optics we will complete during the extra classes. I will tell you the time of the extra classes. In the extra classes, we will complete at the same time the wave optics, and in regular classes we will complete the dual nature, means the modern physics, that is dual nature of matter and radiation and atoms and nuclei. So this is very easy topic. Okay, this is very easy topic as compared to the ray optics. This topic is very easy. Okay, so focus here. So basically radiation have wave nature and the particle nature. So what is the meaning of the radiation? Radiation means light. So light have wave nature as well as the particle nature. So light have wave nature. How we know that light have the wave nature? Because we know that light shows the refraction, etc. So that is why we can say light have the wave nature, because refraction is a property of wave. Okay, reflection and refraction, and there are diffraction also. There is interference also. These are the properties of wave. That is why we can say light shows the wave nature. But at the same time, we will study photoelectric effect. Photoelectric effect. So this photoelectric effect will show us that light will also have the particle nature. This photoelectric effect is based on the particle nature of the light. So we can say light has dual nature, wave nature as well as the particle nature. Okay. So radiation have wave nature as well as the particle nature, means radiation have dual nature. After that, if we will talk about the matter, if we will talk about the matter, so what is the meaning of matter? Matter is something which have mass and has space, that is known as the matter. For example, your mobile phone is matter, your pen is matter. So for matter also, so we know that matter is made up of the particles. We already know that metal is made up of particles, matter particles like electrons, neutrons, and protons. So basically, we can say matter have the particle nature. This thing we already know. This thing we already know. But matter will also show the wave nature. Matter will also show wave nature, and this is proved by the diffraction. Uh, there was an experiment, okay, done by some scientist, Germer and Davison experiment. This is proved by the Davison. We will study this. Davison and Germer experiment. In this experiment, they have proved that electron can show the diffraction, electron diffraction. Nida, why you were absent from so many classes? Hmm? You were absent only for one class. Okay, okay, that's fine. I think that Fawaz was of absent today. So matter has the particle nature because we know that matter is made up of the electron, proton, and neutron. So these are the particles. So matter have the particle nature. After some time, you will see the matter will show the wave nature also, and this is proved by the Davison and Germer experiment, in which they proved that the electron can show the diffraction, not different diffraction. So matter have particle nature as well as the wave nature. So matter have the dual nature. What is the name of the chapter? Matter and radiation. Now you can see radiation has dual nature. Radiation have dual nature. Matter has dual nature. So what is the name of the chapter? Matter and radiation have dual nature of matter and radiation. So this is the introduction of this chapter. This is the introduction of this chapter. So I will start this chapter with photoelectric effect. With photoelectric effect. So now we will see what is the photoelectric effect. Photoelectric effect. So now see what is photoelectric effect. Suppose this is a metal surface, and on this metal surface there are free electrons. We know that in metals there are free electrons because metals are the conductors, and in conductors the current can flow. And why in conductors current can flow? Because of the free electrons. So in metals there are free electrons. So this is some metal surface. On the surface of the matter, on the metal, there are some free electrons, and these are the radiations striking on the metal surface. These are the radiation of high frequency or low wavelength. So basically these are the radiations. These are the radiation. So these radiations are striking on the surface. So due to these radiation have the energy. This radiation will have the energy, means the energy is striking on the surface, and this energy is provided to the free electron, so that after getting the energy the electrons are ejected out from the metal surface. This phenomena is known as the photoelectric effect. Photoelectric effect. And the ejected electrons are known as the photoelectrons. These ejected electrons are known as photoelectrons. Yeah, so this can be explained by assuming that this can be explained by the particle nature of the light. We will assume that here it is assumed that this light rays or this radiation consists of photons, is made up of photons. So there are some photons like this. So what is this? What is this? This is photon. So basically, uh, these radiation is made up of photons, or these photons are also known as wave packets or quanta. Okay. Sometimes this is also known as wave packets or quanta. So now you can say that these photons are striking on the electron, and due to the collision of photon and electron, electron is getting some energy and ejecting out from the surface. So basically photoelectric effect is proving uh, particle nature of the light. So basically this is the photoelectric effect. You are providing the energy, you are providing the radiation, and radiation consists of the photons, and these photons are striking on the electron, and this electron is ejected out from the surface, and this phenomena is known as the photoelectric effect. Now there are certain points. Light consists of wave packets called photons. Light consists of wave packets called photons. So this is the light or radiation. This is made up of photons. Okay, this is made up of photons and or wave packets, you can say. Sometimes these are known as the energy packets or quanta. After this, the mass of the photon is not defined in sense of the Newtonian mechanics. Basically, you can say like mass is 2 kg of some object, like 3 kg. So for uh, those objects, we have some mass. But in case of photons, the mass is not defined. In case of the Newtonian mechanics, with respect to the Newtonian mechanics, the mass is not defined of photon. Now, if we say that these photons are at rest the mass of the photon is defined, and at rest the mass of the photon is zero. So rest mass of photon is zero. After that, all photons travel with 3 into 10 to the power 8 meter per second in air or vacuum. What is 3 into 10 to the power 8 meter per second? Speed of light in air or vacuum. So all photons travel with the speed of light in air or vacuum. Photons are neutral in nature. So photons are neutral in nature means photons do not have any type of charge, either positive or negative. They are neutral. Each photon have definite energy and definite momentum. So basically these photons have energy as well as momentum. So energy of photon is given by energy of photon. I will represent it with capital E, is given by hc lambda, or it is h into f. What is h? H is the Planck's constant. H is the Planck's constant, and the value of Planck's constant is 6.626 into 10 to the power minus 34 joule second. What is lambda? Frequency, wavelength of the incident radiation. This lambda is the wavelength of the incident radiation. What is f? Frequency. Of incident radiation. Frequency of incident radiation, and h is the Planck's constant. So this is the energy of photon. Now momentum of photon is given by momentum of photon is given by momentum is represented by p, and this is given by Planck constant divided by lambda. So you have to remember what is the energy of photon, hc by lambda, or it can be written as HF also, HCy lambda, or it can be written as HF also. H is the Planck's constant. Lambda is the wavelength of the incident radiation. F is the frequency of incident radiation. After that, there is one more point. All collision between photons and matter particles means like electron, are perfectly elastic. So these are the photons. These photons are striking on the electron, means so these are the photons. These photons are striking on the electrons. These photons are coming here, and these photons are striking on the electron, means there is a collision between the photon and the electron taking place here. And this collision will be the elastic collision. Elastic collision means the momentum, initial momentum of the electron and the photon is constant, and the initial and the final momentum of the electrons and the photons is same. Means the momentum is constant as well as the kinetic energy will remain constant. So all collision between the photons and matter particles like electrons are perfectly elastic. So perfectly elastic means initial momentum is equal to the final momentum of the system, and initial kinetic energy is equal to the final kinetic energy of system. Okay. Now this is important point. This is important point. On increasing the intensity of radiation, on increasing the intensity of radiation, radiation means light. If you will increase the intensity of radiation, the number of photons increases, but energy of each photon does not change. If you will increase the intensity of radiation, okay, if you will increase the intensity of radiation, the number of photons increases, but energy of each photon does not change. For example, I am having a yellow bulb of 50 watt and another yellow light bulb having 100 watt. Two bulbs we have, one is of 50 watt, another is of 100 watt. Now both bulbs are yellow bulbs, means lambda of both bulb will be same. Lambda of both bulb will be same. Now both bulbs are of 50, one bulb is of 50 watt, another bulb is of 100 watt. So I told you power is basically intensity. Power is energy per unit area per unit time. Sorry, power is energy per unit time and intensity is energy per unit area per unit time. So basically you can say that if power of this bulb is 50 watt, if power of this bulb is 100 watt, means this bulb will have more intensity and this bulb will have the less intensity. So in terms of the intensity, this have the more intensity and this have the less intensity. Now can you say that this 100 watt bulb will give some light of red color, or this 50 watt bulb will give light of any other color? No, Both bulb will give the light of yellow color. If both bulbs are giving light of yellow bulbs, means the wavelength of the light will remain same. And if the wavelength is same, then energy of photons will remain same. Energy of photons will remain same because wavelength is not changing. What is the energy of photons? Energy of photon is hc by lambda, or it is h into frequency. Lambda is not changing because yellow color bulbs are there. Color of the bulb is not changing. Frequency also not changing. Yellow color will have some specific frequency. Intensity is changing here. This bulb will have more intensity. This bulb will have the less intensity. Okay, so actually, in actual what happened, this 50 watt bulb have the less intensity. This will give less number of photons per unit time. This will give less number of photons. But this 100 watt bulb will give more number of photons. Will give more number of photons. But each photon will have each photon will have same energy. So this bulb will give less photons. This bulb will give more photons. But you can see here number of photons are increasing when the intensity of the bulb is increasing. But the energy of, if you will calculate the energy of each photon, that will remain same. That is not changing. So you can say that on increasing the intensity of radiation, the number of photons increases, but energy of each photon does not change. Okay, so first write down uh, this, then we will discuss next topic. Hamza, are you means understanding? Smita, understanding?
Yes, sir.
Okay. So this is very easy chapter. Follow these lectures properly. Okay, fine. Okay, Hamza, please take the screenshot. Okay, take this. Done. Okay. Photoelectric effect is what? Energy means photons are incident on the surface and electron are ejecting out. Take the screenshot. Okay. Done. Okay. 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 Okay, fine. Now we will discuss work function. Work function is represented by phi. Okay. Work function is represented by phi. So again, this is a metal surface, and these are the free electrons. So you are giving this photons. Okay. These are the, what is this? These are the radiation. So radiation, or this is light, you can say. This is made up of photons, and photons have energy. Means you are giving energy to the electrons. That is why the electrons are ejecting out. That is why the electrons are ejecting out. But how much energy is required by the electron to eject out? So the minimum amount of energy required by the electron for the ejecting out is known as the work function of the material. Work function of the material. For example, if I say that this metal surface have the work function of 2 electron volt, okay, and I am giving the photons of energy 1 electron volt. I am giving energy 1 electron volt, but the work function of this metal surface is 2 electron volt. What is the meaning of 2 electron volt? Mean at least you have to give 2 electron volt to eject 1 electron from the surface. So if you are giving 1 electron volt, so there will be no ejection of electron. Okay. After that, if you are giving 2.5 electron volt, if you are giving suppose 2.5 electron volt, then in that case electrons may come out. May come out. It is not necessary. If you are giving an energy which is more than the work function of the metal surface, then always the electron will eject out. Why? Because suppose you have given energy of 2.5 electron volt. 2 electron volt energy will be spended. 2 electron volt energy will be spended for the work function. Okay. For the work function, 2 electron volt energy will be spended. Now, what is the energy? Suppose you have given to this electron, you have given the energy of 2.5 electron volt. For this electron to eject out, the energy is this 2 electron volt. You have given 2.5. Now, this electron takes the energy of 2.5 electron volt, and after taking the energy of 2.5 electron volt, 2 electron volt is spended to overcome the work function. Now this electron will have an energy of 0.5 electron volt. Now if suppose this electron is ejecting out, is just ejecting out, is at the verge of ejecting out. Now if this electron is at the verge of electing out, there are other electrons also on the surface. Suppose this electron is collided with the other electron, and in that collision, that 0.5 electron volt of energy is spended. So now will the electron will eject out? No, because the electron have the energy of 0.5 volt to eject out. The electron has spended that energy. The electron has expended that energy in collision with the other electron. So that is why it is possible that if you are giving the energy which is greater than the work function of the metal surface, so may the electron come out or may the electron will not come out. So if I am assuming that, there if I have given energy to this electron 2.5 electron volt energy I have given, 2.5 electron volt energy I have given to this electron, and 2 electron volt energy is expended to overcome the work function. And if there will be no collision of this electron with other electron, means this electron still have energy of 0.5 electron volt. That 0.5 electron volt energy will become the kinetic energy of the ejected electron, kinetic energy of this ejected electron. So work function is the minimum amount of energy required to eject an electron from metal surface is called the work function, and work function is depending upon the nature of the metal, what type of metal is there. For different metals the work function will be different. For different metals the work function will be different. You can see this is the work function in electron volt. Basically, what is electron volt? Electron volt is the unit of energy. Electron volt is the unit of energy. So these are some metals, and of those metals, these are the values of work function. Now, for cesium, the work function is 1.9. For potassium, the work function is 2.2. For copper, 4.5. Means to eject an electron from the cesium surface, at least this much energy you have to give. For eject the electron from the potassium surface, you have to give at least 2.2 electron volt energy. Now this I have explained. If we supply energy, E is the energy here. And what is phi? Phi is the work function. If we supply energy greater than the work function, it is not necessary that electron is ejected out of the metal surface. I told you why, because there can be the collision of electrons also, and in those collisions the energy will be expended. So if supplied energy is greater than the work function, electron may come out. Not 100% we can say that electron will come out. Okay, work function is this. After this we will discuss maximum kinetic energy of the ejected electron. So now I told you here, if you are giving some extra energy, that at extra energy, if there will be no collision of electron, that extra energy will be the kinetic energy of the electron. Okay. Suppose this metal surface have the work function of 2 electron volt. Suppose this metal surface have the work function of 2 electron volt, and you have given the energy of 8 electron volt. You have given the energy of 8 electron volt. Now to this electron, suppose to this electron you have given the energy of 8 electron volt, and to eject it will spend 2 electron volt to overcome work function. And if there will be no collision of this electron, then 6, because 2 is expended, remaining energy will be 6 electron volt. So this 6 electron volt energy will energy the electron will have, and that energy will be the maximum kinetic energy. That energy will be not the kinetic energy, that will be the maximum kinetic energy. Why I am saying maximum kinetic energy? Because here we are assuming that this electron will not have any collision with the neighboring electron. If suppose you are providing 8 electron volt to this electron, so what happened? 2 electron volt suppose is expanded in to overcome the work function. Now what energy is remaining? 6 electron volt energy is remaining. Now this electron have some collision with the neighboring electron. Some energy will be wasted there. So the remaining energy now will be less than the 6 electron volt. You can see here. Suppose first condition, you have supplied 8 electron volt to the electron. 2 electron volt will be overcome for the work function. Suppose in collision no energy is wasted. So how much energy left with electron? 8 minus 2, that is 6 electron volt energy will 6 electron volt energy will be there, and this 6 electron volt will be the maximum kinetic energy. If you are providing 8 electron volt and 2 electron volt is used to overcome work function and 3 electron volt is wasted now in collision, so what will be the remaining amount of energy? 8 minus 5, that will be 3 electron volt will be the kinetic energy this time. Now this kinetic energy will not be the maximum kinetic energy because here 3 electron volt is wasted in collision. Suppose you have provided 8 electron volt, 2 electron volt is expanded to overcome the work function. 6 electron volt is expanded or wasted in collision. Now what will be the energy of the ejected electron? Zero this time, because 8 electron volt is used. Now ejected electron will have zero kinetic energy. Now if this is a case, suppose 8 electron volt you are providing, 2 electron volt the electron uh, will use to overcome the work function. Now that electron has expanded 7 electron volt. Is this possible? This will not be possible. This case will not be possible. Why? Because electron has expanded or wasted 7 electron volt already in collision. Okay, so it will have only one, because here the energy conservation will not valid. You can see you are providing 8 electron volt. Suppose 2 electron volt is wasted in 2 electron volt is used to overcome the work function, and 7 electron volt is wasted in collision. Now total energy here will become 9 electron volt, but you are providing 8 electron volt. So means there will be no ejection of electron. Okay, so you can not say what will be the kinetic energy of the ejected electron, because the kinetic energy of the ejected electron will depend upon how much amount of energy is wasted in collision. But you can comment on the maximum kinetic energy. Maximum kinetic energy of the electron can be written as energy provided minus the work function. You can see E minus phi is equal to maximum kinetic energy. So you can say maximum kinetic energy of the ejected electron can be written as E minus phi. E is the energy supplied or energy of photon. So now for this equation, you kinetic energy maximum, you have E minus phi. Now E can be written as HF minus phi, or this can also be written in this form, HCy lambda minus phi. This is known as the Einstein photoelectric equation. So basically, this photoelectric effect is given by the Albert Einstein. Okay, this photoelectric effect is given by the Albert Einstein. He got the Nobel Prize also for the photoelectric effect. There are contribution of other scientists also, but the main work is of Albert Einstein. So Albert Einstein got the Nobel Prize for this. Okay, so maximum kinetic energy of ejected electron will be this. So we will use this relation. Okay, what is E? E is the supplied energy or energy of photon. Okay, so take the screenshots. Take the screenshot. Nida and Hamza. Okay. 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 Done, Nida? Hamza?
Yes, sir.
Okay. Nida completed? Okay. Okay. Okay, just give me 1 minute. Okay, 1 or 2 minutes. Okay. So now you can see here for the electron emission, there is a minimum amount of energy required, and that minimum amount of energy required is known as the work function. In the same way, there is a minimum value of frequency required of the incident radiation to eject the electron out. That frequency is known as the threshold frequency. The minimum frequency of the incident radiation which may cause the photoelectric effect. If the frequency of the incident radiation on the metal surface will be less than that frequency, there will be no photoelectric effect. What is the photoelectric effect? No ejection of electron will be there. So threshold frequency is this. Now for the ejection of electron, for the ejection of electron, we know that minimum energy given for the emission of electron, either you should go give energy greater than the work function of the metal surface or equal to the work function of the metal surface. So E is the energy of the photons that you are giving, and phi is the work function. So E must be greater than or equal to phi. We know that what is the value of E in terms of the frequency. E is equal to H into F, and this is greater than or equal to phi. So frequency can be written as phi divided by H. Frequency of the F is the frequency of the incident radiation. So frequency of the incident radiation either greater than this value or equal to this value. So what will be the minimum frequency? The minimum value of frequency will be phi by H. And this minimum value of frequency is known as the F naught. So there is one more formula you have to calculate work function. Phi is equal to H into F naught. What is F naught? Threshold frequency. F naught is the threshold frequency. Now we can use Einstein energy equation, that will be kinetic energy maximum is equal to energy of photon E minus work function phi. Now we have the value of phi, we can put the value of phi here. So maximum kinetic energy of the photon is equal to E can be written as H into F minus phi can be written as H into F naught. Now there is a equation of a straight line y is equal to mx minus c. Y is equal to mx plus c. But here I am taking minus c because this is minus. C. So basically why I am writing this, because I want to draw the graph between the maximum kinetic energy and the frequency of the incident radiation. So if you will draw the graph between y and x, so m is the slope of the graph and minus c will be the intercept. Minus c will be the negative intercept on y-axis. So this kind of graph you will get. Kinetic energy of maximum kinetic energy of electron, frequency of the incident radiation or photon. So this type of straight line graph you will have, and this value will be the negative intercept. And what will be the value of the negative intercept? C is the intercept. Minus HF naught. Okay, minus HF naught. It will be H into F naught. So I am not taking minus sign because already this is in below the x-axis. This is x-axis, this is y-axis. So this type of graph we will have, and this value will be the threshold frequency. After this frequency, there will be the ejection of electron. Okay, if the frequency of the incident radiation will be less than this value, then there will be no electron emission. Then only there is the kinetic energy. Okay. Now after this we will have the threshold wavelength. We will have threshold wavelength. So threshold wavelength is the maximum wavelength or the longest wavelength of incident radiation which may cause photoelectric effect. In the same way, we can calculate the threshold wavelength. See, threshold wavelength lambda naught. Threshold wavelength is represented by lambda naught. So the longest wavelength of incident radiation, which can cause photoelectric effect, Okay. Now we know that for for electron emission, this will be their energy provided must be greater than or equal to work function of the metal surface, and E can be written as hc by lambda, and that is equal to greater than or equal to the work function of the metal surface. Lambda from this equation you can find the lambda. So lambda will become this, and this lambda is either less than this value or equal to this value. So maximum value of the lambda will be hc by phi, and this maximum value of lambda will be the lambda naught, threshold wavelength. So phi you can calculate from here. So you will get one more formula for phi, hc by lambda naught. Now you can use Einstein's energy equation, kinetic energy equation. Maximum kinetic energy of the ejected electron can be written as E minus phi, and E can be written as Sc by lambda, and phi can be written as Sc by lambda naught. Now we will plot the graph between the maximum kinetic energy and 1 by lambda. Maximum kinetic energy and 1 by lambda we will plot the graph. So we can compare this equation with y is equal to mx plus c again. Okay, it will be minus c because this is the minus intercept. So you will get the graph between the maximum kinetic energy and 1 by lambda. This type of graph you will get. Here is the maximum kinetic energy on this axis. Here is the 1 by lambda of the radiation. Okay. Now this type of straight line graph we will have because we have the equation y is equal to mx plus c. What will be the slope? M. Slope will be hc. Slope of the graph will be hc. This angle is theta. Slope of this graph is also tan theta, and it is also hc. Okay. And this intercept is negative intercept is hc by lambda naught. Hc by lambda naught. So in case of threshold frequency also, we can calculate the slope. So if this angle is theta, slope of this graph will be tan theta, and this slope uh, from here you can calculate. You are plotting the graph between the maximum kinetic energy and the frequency. So h will be the slope. This m will be the slope. You will compare this equation and this equation, and you will get h slope is equal to h, Planck's constant. Take the screenshot. Okay. 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 So Hamza, you also completed?
Done, sir.
Okay. Okay. So Nida and Hamza, are you understanding? Means these are very easy things we were doing right now. This chapter is very easy. Okay. Now we will discuss kinetic energy versus intensity. We know that maximum kinetic energy is given by E minus phi, and E we can write HF, phi is phi, and maximum kinetic energy can be written as hc by lambda. So you can say the maximum kinetic energy is depending on the on what factors the maximum kinetic energy is depending. You can remove this equation. Maximum kinetic energy is depending upon the energy of photon and the work function of the metal. If you will increase the intensity of radiation, what I told you there, in the photoelectric effect, what I discussed, on increasing the intensity of radiation, the number of photons increases, but energy of each photon does not change. Means the energy will not change. Energy will not change on increasing the intensity. If energy will not change, then kinetic energy maximum of the electron will remain same, because the work function will also remain same. Until and unless you will not change the metal, type of the metal, type of the metal, the kinetic maximum kinetic energy, the work function will not change. Means this energy is not changing on increasing the intensity. Work function is also not changing. So maximum kinetic energy will also not change. So on increasing the intensity of radiation, you can see this graph. On increasing the intensity of the radiation, the kinetic energy maximum is remaining same. So kinetic energy maximum is independent of intensity of radiation. You can see this graph is independent. Okay, so you can, if you want, then you can add this statement here. I have given one beautiful example also to explain this. Hmm. On increasing the intensity of radiation, number of photon increases, but energy of each photon does not change. Now we will discuss numericals. So before that, I want to tell you something. If you want to calculate the energy of photon, so energy of photon is given by E is equal to hc by lambda or hf. So if you want the energy in electron volt, so for that case you can write this also, 1240 by lambda. So you will get the energy in electron volt. But in this case, this lambda will be in nanometer. Okay. So they are saying work function of a metal, work function of a substance is this 4 electron volt. Find the longest wavelength of light that can cause photoelectric effect for that can cause photoelectric emission. Work function is given, means phi is given, that is 4 electron volt. They are asking the longest wavelength. Longest wavelength. What was the longest wavelength? The longest wavelength of incident radiation which can cause photoelectric effect, that is known as the lambda naught threshold wavelength. Means indirectly they are asking threshold wavelength. Lambda naught they are asking. Very easy. You can calculate the energy either with this formula E is equal to Hc by lambda, or you can use this E is equal to 1240 divided by lambda. You will get the answer in electron volt. So uh, we have one formula, that is equal to work function is equal to, we have this formula basically. Work function is given by Hc by lambda naught. So with this formula, you can calculate, because you have phi, you have value of Planck's constant, c is the speed of light, 3 into 10 to the power 8, you will get the lambda naught. But I am telling you the shortcut, so you can apply this. Phi is what? Phi is the energy in electron volt. It will be 1420 divided by lambda. So you can put the value of phi. Phi is 4 electron volt. It is equal to 1240 divided by lambda. You will put in nanometer. So lambda you will get in nanometer. So lambda naught you want to find. So lambda naught will be 1240 divided by 4. You will get 310 nanometer. What is the use of this formula? This formula will be used like this. For example, again I am telling, if suppose lambda is given as 620 nanometer, and they are saying find the energy in electron volt. If you want to find energy in electron volt, you want to find. So you will directly apply this formula 1240 divided by lambda, and lambda should be in nanometer. So you will write 1240 divided by lambda is 620. So you will get energy of 2 electron volt. Even more question we will do. Okay. So this is a metal surface. On this metal surface, the radiation of wavelength this is incident first, so that the electron is ejected out, and this electron have the velocity of v1, or the speed v1. Now, after some time, same metal surface is there because work function is same. Wavelength, incident radiation of wavelength 310 nanometer is incident on the surface, so that the electron will eject out, and this velocity of ejected electron is v2. Now ratio of the velocity, or you can say speed, is given 2:1, and hc is given this. Find work function. We have to find the work function. We have to find the work function phi of the metal surface. So I am assuming this is the case number 1, or this as the case number 2. So in case number 1, apply this equation E, maximum kinetic energy, Einstein's photoelectric equation. Apply Einstein photoelectric equation. Kinetic energy maximum of ejected electron is equal to E minus 5. Kinetic energy maximum. What is the formula of kinetic energy? Half mv square. So we are applying this maximum kinetic energy for this electron. So it will be half into m into v1 square. Half into mass of electron into v1 square. This is equal to E. E can be written as h c y lambda minus y. So it will be half m v1 square. hc is given as 1240 electron volt nanometer. Electron volt nanometer. And wavelength is already given in nanometer, 248 nanometer for the first case. Minus 5. So you will get half m v1 square. This value, we can cancel this value out with 4. 4 3s are 12, and 4 1s are 4, and this is 0, and 4 6s are, and 4 2s are, and it will be 6 5s are, 62 5s are 310. So it will be 5 minus 5. So this is equation number 1. Now for the second case, for this case, we'll apply the Einstein's energy equation. This second case. Kinetic energy maximum is equal to energy of photon minus work function phi. Work function phi is same because metal surface is same. This is given also in the question. Maximum kinetic energy for the second case is given by half into mass into v2 square. Okay. Energy can be written as hc by lambda 2. Okay. This is lambda 1. You can write. Lambda 1 is basically given as 248 nanometer, I think. 248 nanometer. 248 nanometer. Lambda 2 is given as 310 nanometer. Okay. So it will be minus 5. So it is half m into v2 square is equal to hc is 1240. You can see here 1240 electron volt nanometer, and lambda 2 is 310 minus 5. So half m into v2 square is equal to, when you will cancel this out, you will get 4. So it will be 4 minus 5. It will be 4 minus 5. This is equation number second. Now we can solve the equation number 1 and equation number second. So I am dividing the equation number second, equation number, I am dividing the equation number 1 with equation number second. So equation number 1, we have half into m into v1 square is equal to 5 minus 5, and this is divided by half into m into v2 square. This is divided by 4 minus 5. Now this half will be cancel out, this m and m will be cancel out. So we will have v1 by v2 square, and it is 5 minus 5 divided by 4 minus 5. What is v1 by v2? v1 by v2 is 2 ratio 1, so means 2 by 1. Then write 2 by 1, the square of this. So we'll get 4 by 1, 5 minus 5, 4 minus 5. Now multiply, do the cross multiplication. It will become 16 minus 4, 5. That is equal to 5 minus 5. So from here you will get 16 minus 5 means 11. Minus 5 plus 4, 5, you will get 3, 5. So value of 5, you will get 11 by 3. So it will be 3 3s are 9, and it will be 3 6 are 18. Again you will want 6 6. I think this answer you will get 3.666 electron volt. Because you are getting the value in electron volt, because you have already put this value in electron volt. Okay, so take the screenshot. Done. Hamza completed. Nida completed.
Yes, sir.
Nida completed. Okay, write down this. Where you can. Okay, write down this. Okay, okay. Okay. Okay, so here you have to remember this V1 is the velocity speed. This is also speed. Okay. 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 Nida, uh, got it now? Understanding the numericals part and the theory part. And Hamza? Okay. Good. Okay, Hamza and Nida. Don't miss the next class. We will discuss some topic in the next class, and we will finish this chapter also soon. Okay. And one more thing I want to tell you, maybe uh, there will be one extra class I will take, okay, on Friday. On this Friday, maybe I will take one extra class. I will tell you the timings, okay, and you should join that extra class, because in that extra class, uh, I will start the wave optics, okay, because now your exams are coming, I know, and we have very much less time to complete the syllabus on time. So I'm thinking that I should take the extra class on Friday, and in that class we will discuss wave optics, and in the regular class we will discuss the modern physics, and hopefully we will complete the syllabus on time, so that you can revise the notes properly